Hello everybody, it's a pleasure to participate in this workshop, and today I'm going to give a general review of asymptotic behavior of so-called V statistics. The outline of my talk is as follows. In the first introductory part, I want to give some definitions, main definitions, examples, and to explain the connection of limit theorems. I want to talk about with the classical limit theorems of the probability theory, and also to explain what is the case of canonical kernels of statistics. And after that, I want to introduce two approaches of describing the limit elements in these limit theorems, which are the integral representation of limit elements and representation of limit elements in the form of multiple orthogonal series of Gaussian random variables. And well, I think that as our talks are short, then the fourth part will be omitted, but it says something about the properties of the distribution tails of V statistics and the limit elements as well. And in both sections, I will try to differ a canonical, classical case where the random variables are independent, and the case of my and my colleagues interested when the observations have weak dependency conditions. So, the objects I want to talk about are so-called V statistics, defined here. Both V statistics are generalizations of sums of random variables. Here, x, y are random variables from a stationary sequence observations. N is a sample size, M is dimension of statistics. F is so-called kernel function of statistics, which is supposed to have to be from the appropriate L2 space. And xy star will be the independent corpus of our observations in case where the observations themselves are dependent. So the difference between U and V statistics is in the domain of summation, because here all indexes must be distinct. And for V statistics, they also are called Mises functionals. We sum all over all possible indexes. And the approaches of deriving asymptotic behavior of these two types of statistics are quite similar. An approach which helps with, for example, V statistics will help with U statistics, and so in some sense I will mix these two types of objects together. Here are some examples of two-dimensional V statistics, and we can see that choosing kernel function the appropriate way, we obtain a lot of classical objects which are used in mathematical statistics, such as sample variance, mean difference, and so on. Well-known chi-square and omega square statistics using asymptotic tests. Also, special cases of two-dimensional statistics. So the object is quite popular and quite general. I want to remind two, well, I think most important limit theorems from the theory of summation of random variables. If we have independent random variables, weakly dependent random variables with the same distribution function, and finite variance, then the sum of these random variables up to n, normalized by n, converges in probability to some constant which is equal to the mathematical expectation. This theorem is called the law of large numbers, and if the random variables are centered that means that their mathematical expectation is 0, then we can try application rate of convergence and apply some weaker normalization. And the classical central limit theorem states that if again all summands are independent or weakly dependent, have the finite variance and the same distribution function, they're normalized by square root of n, and they are centered. Normalized by square root of n, we have the weak convergence to the non-degenerate random variable, which happens to be a Gaussian random variable with 0 mean. And for example, central limit theorem is extremely useful in calculating the probabilities of some random variables hitting a fixed set, or in mathematical statistics in pointwise and interval, estimation of unknown parameters, constructing asymptotic tests, and so on. So that is where our motivation starts. When we, for example, consider two-dimensional statistics instead of sum of random variables, then quite similar results hold. Law of large numbers. With such normalization, we have a convergence in probability to mathematical expectation, but if this mathematical expectation vanishes, then we can use a weaker normalization, and using such a decomposition of the kernel function, we can decompose our normalized statistic in such a way and prove that the first summand goes to 0 when n goes to infinity. And for second summand, we can apply classical central limit theorem and again get a normal random variable as a weak limit. But here, for V-statistics, we have one more step. If these functions g, which are denoted in here, are identically equal to 0, then this second summand is 0 again, and we can then consider the first summand and apply a more weaker, normalization, which is n in two-dimensional case, and in this case, we have some random variable as weak limit, but it will be non-degenerate and non-Gaussian. And so, our interest is how to describe the distribution of this random variable. In fact, there are two approaches of describing this random variable, as it was said in the introduction. So, here is the degeneracy condition, which in the previous example means that the function g is 0, and we cannot apply the classical central limit theorem. This is most difficult case, and also it is called canonical because due to the Hövding decomposition, which was derived by Hövding in the 1940s, I think, any V or U statistics can be represented as a linear combination of canonical statistics with such kernels, canonical kernels. And so, if we can solve the problems concerning canonical statistics, we can solve any problems of asymptotic behavior of V statistics. So, here are some important names and dates of people who were describing the asymptotic behavior of canonical U and V statistics, and you can see here that they use two forms of describing the limit element: form of multiple stochastic integrals and form of multiple orthogonal series. Now I move on to describing the weak limits in the integral form. If we introduce such a random measure, so-called standard empirical measure, which is in fact just a number of observations hitting set B, centered and normalized. Then we can represent our canonical V-statistics in such an integral form. It is known from the theory of random processes that for such empirical measures, there exists a limit element, and it is a Gaussian-centered process called Brown and Rich, which is in its turn a linear transformation of the white noise Gaussian process. And so this representations hints that we can have such an integral. Here f is non-random function, and it's m-variate stochastic integral with respect to Gaussian measure. And it was proved in 1983 by Rubin and Vital, by Dinkin and Mandelbaum, that for independent and unequally distributed observations and from appropriate kernel space, in fact, kernel has to be just square integrable on all diagonal subspaces of x power m. Indeed, these limit very false. And this stochastic integral can be interpreted as an L2 limit of corresponding integral sums. So we are also interested in the weakly dependent case. Throughout my talk, I mentioned different weak dependency conditions of mixing type. I will not explain in details what they are and how they differ from each other. Psi mixing, phi mixing, alpha mixing conditions are just different types. Some are stronger, some are weaker, of weak dependency condition. And they mean that if observations are further and further in the sequence of observations, then the joint distribution functions are closer and closer in some sense to the product of the distribution function. So they're closer and closer to independence. The classical M-dependent case where two observations are independent if the more distance between them is more than m in the sequence of observations. It's just an example of this mixing condition. So in the mixing condition, the limit process for empirical standard measure is again a Gaussian process, but not a Brownian bridge. It's a more complicated form. Here we can see its covariance function, where fj are joint distribution functions of observations x0 versus j. And so we can expect that the multiple stochastic integral with respect to increments of this Gaussian process must be a weak limit for the sequence of canonical V-statistics, for example, in the mixing case. And unfortunately, there was no general integral construction, and we didn't know what are proper kernel space to define this stochastic integral as L2 limits of the corresponding integral sums, but this general construction was described by me and my supervisor, Professor Parisa. And this construction was used to define such weak elements, and the conditions were found under which indeed the sequence of canonical for music statistics converges in distribution to such multiple stochastic integral. And I want to say a few words about the other approach, which is of decomposing the kernel function into the multiple orthogonal series and solve the limit elements again has the form of multiple orthogonal series. This is the first result. So the result of Mises, who described an asymptotic behavior of canonical V-statistics in terms of series of Gaussian random variables. Here we have these are basis functions, and we can use such a decomposition of the kernel function. And using this approach, we can move limit theorems for the sequences of U and V statistics respectively, and under some conditions of kernel function, we have convergence to such multiple orthogonal series. Here F are coefficients and tau are centered Gaussian random variables, which in the case of independent observations are independent, and in the case of weakly dependent observations they are dependent. So the first result, independent case, is classical, was derived by Rubin and Vittel in 1980, and the result in the weak dependence and the weak dependency condition is quite up to date. And here we can find the connection between these dependent Gaussian random variables which participate in the describing of limit element, and analogous limit theorems can be proved for U statistics as well. Here the form of limit element is a little bit more complicated. Here we have some so-called weak products, which are infinite products of Hermite-Chebyshev polynomials of the same Gaussian random variables as in the previous theorem. And again, they are independent if the observations are independent, or we can just write down the covariance functions in the case of weakly dependent observations. So these two approaches doesn't cover each other. They are different from the point of conditions on the kernel function and the distribution of observations. So each approach has its own advantages. And I think I'll stop here. Thank you for your attention.
Thank you very much. Any comments?